Good afternoon, ladies and gentlemen. Welcome to today's webinar hosted by Micronit. And before we are going to the actual slides of today's webinar, I'm going to make a few announcements. So this webinar is hosted live, and you can ask your questions anytime during the webinar via your Q&A chat, which you can find in the upper right screen within the Teams environment. What we'll do is that I'll first go through the slides, and at the end of the slides, we'll hold a live Q&A session. I'm already going to tell you that we will probably not be able to answer all of your questions, but we will make sure that we will follow up on all of your questions after the webinar. All right, so let's go over to the presentation of today with the title Adding Value by Making CMOS, MEMS and Fluidics Meet. And just for a little bit of introduction, with CMOS, we are talking about the complementary metal oxide semiconductor used for construction of ICs or integrated circuits, used to make devices, analog circuits, image sensors, data converters, and RF circuits. And today or tonight, depending on where you are, we're also going to shortly go into hybrid platforms. For instance, a platform in where we combine circuits in integrated circuits with photonics. Also a very, very interesting trend. All right, so a little bit about me. My name is Joost Dierven. I'm one of the business development managers at Micronit, and I'm focusing on our glass and silicon activities. So you could say I'm focusing on our MEMS activities, as well as some of our fluidics. I'm not alone during tonight's webinar, although you will only see and hear me. I'm actually here with some of my colleagues, and I've made I've added two of them in this slide. On the left, you see Jeroen Haneveld. He is one of our process architects, and here on the right, you can see Marco Blom, who is our CTO. And this team of fairies will help me answer all of your questions, so that I can focus on the slides for now, and we will follow up on the questions, also offline, in case there are more questions than we can handle today. I also added my contact details should you feel the need to reach out to me. There's our general email address here depicted, info@micronit.com, for all of your general questions. But should you want to connect with me, there's also my email address depicted on the left bottom side of the screen, which is my name @micronit.com. I'll also share my email address and our contact details later on in the presentation, should you have forgotten the correct email address. All right, content of today's webinar. I've made a few chapters, and between each chapter, I'm going to pause just for a second to make sure that we're all aligned. I'm going to start with a few facts about Micronit, and then I'm immediately going into some of the materials and technologies that we provide, and this could all be considered the introduction. And after that, I'm going to talk about the most important market drivers driving the need for integration. And then before we go to the Q&A session, I'm going to talk about some of the enabling technologies which we provide to integrate devices. And finally, I'm going to show some which is actually part of this chapter. I'm going to show you some cases, some examples. After that, we're going to go to the live Q&A session, and well, then that's it for today. So I hope you stay with me for the next roughly 45 minutes, and let's start off with the first chapter. So the first chapter about micronits, some key facts. And before I'm going to talk about when we were founded and these kinds of things, I'm going to share you our vision. And our vision is quite relevant for the rest of the presentation. So that's why I'm going to stop here for a bit. So our vision is that we believe in a future where people age healthily. And this means that we're going to talk about medical devices later on, but I'm also going to hit some drivers in the area of the life sciences in general. To execute our vision, we've defined a mission, and the mission is as follows. We want to be the leading innovator and global partner in design, development and manufacturing of customer-specific lab-on-a-chip solutions for the life sciences and, well, it's highlighted here again, health applications. Some key facts. Micronit's founded in 1999. We have 2 locations, one in Enschede, the Netherlands, and one in Dortmund, Germany. We serve over 1,000 customers in roughly 50 countries. This is just an example of companies and diagnostics and industries we serve. So we work with the top 25 of these, let's say, of the companies in these areas, as well as work with the top 10 technical universities. We are to date, and I checked it with our HR department, with 140 people from different areas, in making sure that we can integrate biology and fluidics, so physics, on chip, and obviously we need personnel to manufacture products. We are quite a multinational company because our employees are to date coming from 15 plus nationalities. We are ISO 9001 and 13485 certified, and obviously the latter is there to serve our mission and vision for medical devices. So this was the key facts of Micronit in a glance. And I'm now going to talk about some of the materials and technologies that we provide as an introduction of today's webinar. So Micronit actually processes 3 categories of materials, and I've categorized them in glass, silicon, and polymers. And we also create hybrid devices of these materials, which is obviously today's topic. So if we divide those 3 categories again in process or microfabrication technologies, we end up with a slide which looks like this. Here I grouped some technologies, as you can see here. So for glass and silicon, you obviously use a different wet etching process, but you can still use wet etching to create your structures. The same is true for dry etching. And technologies like deposition and bonding and lithography are for both grouped as well. Then we have a set of technologies used for polymer processing, which is quite different than glass and silicon in terms of technologies. So embossing technologies, but also a more rough variant in the form of micromilling, as well as injection molding, which we do together with partners, which I'm going to present to you in a bit. And of course, also these polymer parts need to be bonded. So bonding is again a key element. And then last but not least, when we have these microfluidic chips, we also need to provide some, we also feel we should provide some general or back-end technologies to integrate biology in the form of reagent deposition, but also to integrate sensors in the form of flip chip bonding, for instance, or to influence the surface area, the surface of the chip by applying a coating to prevent biofouling, for instance. Last but not least, we have to look at dicing and packaging as an integral part of delivering components to our customers. All right, so now we've basically looked at the microfabrication technologies and Micronit grouped into the glass, silicon, and polymers. And now I'm going to hit the topic of bonding a bit, because bonding is a key enabling technology for creating hybrid devices. So Micronit has a lot of knowledge on bonding materials, and different materials and material combinations can be bonded together, mostly direct and thus without adhesives or intermediate layers. Also, some of the bonding technologies are done at room temperature or low temperature in order to allow integration of organic materials. So here on the screen, I made a thermometer, and we go from the room temperature to very high temperatures. And first we hit the topic of laser assisted bonding, which can be done at room temperature. For the sharp listeners of today's webinar, this actually means that locally you're obviously going to go to higher temperatures to make a bond, but overall you can say it's a room temperature way of bonding, and organic materials or biological material can survive this process, thus allowing for biofunctionalized surfaces. So going up the temperature, moving up the ladder a little bit, we end up at patentable adhesive bonding. This can be done in the form of a spin-on resist or a dry film resist, for instance, to bond glass or silicon to CMOS wafers at relatively low temperatures, allowing the preventing damage to the CMOS, to the integrated circuits. Moving up the ladder even a little bit more, we end up at eutectic bonding using a metal layer. In this case, for instance, to use gold to bond gold, to make gold silicon connections. Moving up the ladder, we're almost there, by the way. So here we are with anodic bonding, allowing us to bond glass and silicon, or glass and metal layers to each other, and ending up at the very high end of the thermometer, we end up at direct bonding glass to glass, or glass to silicon, or even polymer to polymer. Let's also not forget that we can bond silicon to silicon this way. Now, I've talked about some of the technologies that Micronit offers, but we realized that we realized very well that just focusing on our own technologies is not sufficient to create complex or hybrid devices. So therefore, I have two examples of our ecosystem, you could say, in where we collaborate here on this slide in an alliance. We call ourselves the Flow Alliance, and we focus on polymer parts together with two Dutch companies, Axicon and Helvoet. And together with these companies, we can basically provide the design, engineering, and manufacturing. So from concept to manufacturing in every phase of your project. The second example that I'd like to share with you is our collaboration with an institute. So not to commercial parties, but to an institute, namely Fraunhofer EMFT. And we collaborate with them on the, well, actually what's depicted here. So this is a piezo-driven MEMS-based micropump, which is a platform that Fraunhofer developed and which can be adapted for quite a broad set of parameters. And the nice thing about this collaboration is that we have all the design and engineering, but as well as the industrialization know-how in-house to bring this product to the market but also with the right ISO certification in place. And according to the newly introduced, or at least the newly in effect, medical device regulations, which came into effect earlier this year. So some of the unique selling points of this collaboration, I've named a few of them already. So we can basically together we can modify the platform to your needs, but also together we have the test capabilities in house to make sure that we can also verify whether the design changes cover your needs. In collaboration, we can provide guidance for the initial feasibility studies up to the product development and basically the implementation, the industrialization for instance, medical class 3 implants. And then a first unique selling point is that Fraunhofer and Micronit have a little bit more know-how than just the platform in itself. So we can also assist you with providing components or system solutions besides just purely the component. And one of the I've mentioned a few applications of such a pump. So an implant used for drug delivery, for instance, for cancer treatment, but also an artificial sphincter system. All right, so we finalized our introduction on the on Micronit, its key, some of its key facts, and as well as our basic set of technologies for the 3 different materials, some general back-end processes, and the need or the example of the Flow Alliance and the collaboration with institutes to show you and to tell you that besides let's say our own drive for technology innovation, we think it's we are convinced it's extremely important to collaborate with parties, or each focusing on their own strengths, in order to make even more hybrid combinations of different materials, but also of different components, components from the microfluidic world, from the MEMS world, and the CMOS world. And for this chapter, I'm now going to go into some of the market trends, and these market trends, I'm going to highlight 3 of them are the main drivers for integrating all of these components into one system. So this is a full slide, and I'm just going to talk about a few of these topics in more detail. So I'm going to talk about DNA sequencing to start off with. I'm going to talk about personalized medicine, and I'm going to talk about decentralization. And with decentralization, I mean the decentralization of healthcare. So they are linked to the topic of personalized medicine. I'm not going today talk about cell sorting analysis. I'm also not going to hit the topic of automation and towards instrument free. I'm just going to focus on these 3 here. Basically, before I start off with explaining what personalized medicine means or decentralization means, I'm going to go to a small animation. Because these topics, so the topics of DNA sequencing, personalization of healthcare, and the decentralization of healthcare, they are the main drivers for us to integrate microfluidics and MEMS, which we can do in-house, but also integrate them with CMOS components, which we for which we would need to partner up to create systems with a higher value. So the first market driver, which I'm going to talk about now, is the DNA sequencing. And here I depicted a slide from Yole development presented in a report from them from April 2019, and we can see the, let's say, a market which is mainly based on glass flow cells. And this here I just added an example of a glass flow cell. This is an example of a flow cell from Illumina. And we basically see a trend. So Yole observed the same thing to, well, first of all, a growth in general, in absolute sense, but also in a relative sense, an increase in silicon glass flow cells. And there are actually a few reasons why we see this increase in hybrid flow cells. So one of them is really technology driven. It is an example of a nano printed patterned flow cell, resulting in higher data output using the same flow cell. And then on the right top of your screen, so here it is, there is an example of a flow cell actually which makes use of CMOS based sequencing. And this is also an increasing trend in DNA sequencing. This is an example of the iTorrent just taken out of the internet. But there are more parties working on a approach in where CMOS is used. The second market driver that I want to highlight is the personalization of healthcare, which means that that there is more focus on giving the right treatment to the right group of patients at the right time, instead of just devising one therapy and using that for the entire group, which can be seen here on the screen, which is just a visual representation of what I just said. So a treatment for everybody and a personalized treatment, making groups or even targeting individual patients and adjusting the therapy to their needs based on biomarker diagnostics, for instance, after analysis of blood, DNA, urine, or tissue. And the personalization of healthcare means more diagnostics, and more diagnostics or more complex diagnostics demand an increase in functionality on basically not purely from the instrument point of view, but also bringing the functionality to the consumable, to the chip. And then this increase in functionality, translates in the demand to integrate several materials or even separate components on the same base. I'm going to talk about form factor, because obviously form factor plays a role next to just purely the material, as well as the demand that if you want to basically bring all these functionalities to your consumable, you need to decrease your functionality itself. So the overall size of the functionality. The third and final market driver that I'd like to address is the decentralization of healthcare, and this is quite an important one for DNA sequencing, moving towards, for instance, the MySeq platform provided from Illumina, which is the first FDA-regulated platform used for the let's say the IVD market, in order to allow for personalized medicine, as depicted on the previous slide. And the trend is basically that we see that the big functionality, the big instruments in the laboratory, are moving to slowly towards a situation in where patients can monitor certain parameters at their convenience of their own home, which obviously means that you need to devise a device that allows for use not by untrained personnel instead of basically personnel using equipment in the laboratory, the ICUs or the ER, and to translate that into devices. I've made a few. I've just picked a few out of the numerous ones. So I started out with the example of the platform provided by Illumina, which moved to IVD. But there are, if you go down to the latter, to the latter, basically moving towards the home situation, we come across the Gene Expert system provided by Sepite, but also the near patient use device provided by Abbott, the iStat. It's a widely used device which provides medical personnel with immediate feedback. So the measurements only take a few minutes, and they can adjust basically their treatment right near to the directly near to the patient, directly next to the bed of the patient. And I've seen this tool to be used in the intensive care. Myself and my daughter had to stay at the intensive care for about 6 weeks, and I can say that it literally saved a life at that point in time, because the personnel was able to immediately change the treatment given to my daughter. All right. So now we've covered quite a few topics already. So we talked about some of the key facts of Micronet when we were founded and so forth. Some of the technologies that we provide. I've given you a bit of an introduction in the most important microdrivers for the need to increase to bring more functionalities to the chip or to the lab on a chip. And now I'm going to talk about the enabling technology. So what do we need to do in order to make sure that we can provide all of these technologies on a lab on a chip device? And I'm going to hit off with a slide, a very full slide on platform technologies from a wafer level point of perspective. So we're not going to talk about different form factors here. We're really going to talk about matching form factors, creating wafer level packaging, or creating fluidic layers on top of CMOS. Our starting point is a silicon wafer, which is either a CMOS or a MEMS device wafer, which we are going to basically use as a scaffold to add functionalities on. On the left side here, we see actually a few things. So what do we need to do in order to increase functionality? We need to be able to pick and place several components to add components on top of our MEMS or CMOS. We need to, which is of course a different form factor in this case, but just one example. And in order to make sure that we connect to the pick and placed component, we need to be able to deposit patterned RDLs or redistribution layers on top of our MEMS or CMOS or biosensor wafer. And I've also made a example here in where the backside processing plays a role. So we call it the LBE, so the localized backside etching, in order to, for instance, to open up grids like depicted here on this picture, to open up the waveguide grids on a CMOS or actually a bi-CMOS platform, in where integrated circuits and waveguides can be found on one wafer, on one scaffold. Now, that is really the, let's say, MEMS and CMOS talk, but we can do more than integrating MEMS and CMOS, or adding value to CMOS by LBE processing, or, for instance, non-CMOS compatible metallization. And an example of that is, for instance, gold, which is often used for bio applications. We can also, or actually but with we, I mean a very important platform technology is also to provide fluidics on top of CMOS or MEMS. In this case, an example is shown of a glass microfluidic layer, which serves as a packaging too, with top connector holes in order to make a connection between the outside world and the micro world. And here on the bottom you find actually a picture of a fluidic layer on top of CMOS, but this is not created by glass, but with a dry film resist in this case, and where micro well structures are created and allowing for individual chemical or biochemical process to be basically, or reactions to be in place in the individual microwells and to assess them individually. And then thirdly, we have the more, well, the packaging example. So we basically to make sure to provide sturdiness to a certain component, like here depicted on the right side of your screen. This is a packaged lens, a packaged lens wafer, of actually where a micro lens is packaged in a glass cavity wafer, using a dry film resist again to bond these materials to each other. And this basically this application was used for a medical imaging application, but of course wafer level packaging can be used to create micro LEDs, or to package all kind of different components. Here I've just depicted a very straightforward way of packaging, just using a glass cavity wafer on top of my MEMS or CMOS wafer. But you can also think to integrate RDLs again, or to make electrical connections to the outside world, making use of TGV wafers, through glass vias wafers. So now we've covered basically a whole set of platform technologies that Micronit provides in order to make hybrid components, making use of a wafer level set of technologies. And one of the examples, which I'd like to go into a little bit more detail, is a collaboration with IMEC. IMEC is an international research and innovation hub on micro and nano electronics, and for this collaboration, we are basically the project is called Internet of Water, so IOW Flanders. So Flanders is the Dutch-speaking part of Belgium, in where basically in where this is a nice example of integration of a silicon wafer with all kinds of functionalities. So it's a biosensor wafer, in where we can measure different parameters in water, and on top we have 2 layers of glass, which basically provide a well, which can be seen here, a separate component, right, in order to have a reference measurement, as well as the inlets for the water to be analyzed. And I've added a few pictures on this slide. So this is an example of the product, the glass silicon hybrid product. And this product is then integrated into a a tube like is depicted here, and the final device, well, it's just basically the control of the measurement unit, with a nice basically a nice a cabinet enclosing the control. Basically forms the sensor hub. Now, what do we want to do, or what does IMEC want to do in collaboration with all its partners? The goal is to create a fine-grained sensor network over the, let's say, in Flanders. In this case, we're talking about more than 2,500 sensor hubs to be deployed in all areas of Flanders, as well as monitor not only, for instance, surface water, but also look at the wastewater before treatment and after treatment. And this provides a real-life image of the water quality 24/7, and this real-life data facilitates a more dynamic and efficient water management, and it also helps to make predictions of future needs. And this all is driven by the fact that there is a big water scarcity, and we're talking about fresh water here in Flanders. The second showcase that I have for you is a organ on a chip platform, in this case to be used in combination with cardiomyocytes. And this is a nice example of where we need to integrate let's say, different form factors. So before I'm going to talk too much about all the individual components, it is obvious that we have a big microfluidic scaffold. We can see, well, it's actually a little bit difficult to see, but here we see a CMOS wafer, or a CMOS sensor, a CMOS product, which is actually a high density MIA chip developed by IMEC, and a PCB board to control the CMOS chip. Furthermore, we see some cell culture chambers, but also some built-in pneumatic or peristaltic pumps driven by air, in this case by pressure from the outside world. Because of course we have the chip, but we also shouldn't forget the connections to the outside world in form of electronics, in form of fluidics, and also in this case in terms of air pressure. This platform it focuses on applications in pharmacological research, simulating physiological and chemical response of, in this case, human organs. This project is already finished. This subsidy project, but based on it, a new project started, which is the more for medical project, in where even a bigger consortium is working on making a modular smart plate to be used for all kinds of organ on a chip applications. And where again some things are very essential. So we're talking about hybrid assembly, on which Micronet is focusing on. We are looking at integrated microfluidics. So there are well, as you can see, there are wells. There is a microfluidic plate in where, in this case, silicon micropumps have been integrated. There are the actual organ on the chip devices, and where the cells are grown, and the whole thing needs to be controlled. So a printed circuit board is added, including power cells for Wi-Fi, so that it all connects wireless with computers and stuff to monitor the individual organ on a chip devices. And the whole thing needs to be assembled. So yeah, that's basically Micronet's challenge here, with the goal to create an open technology platform under the European project, so the CSEL. this is just an URL order. We'll continue. So all right, something went wrong with my presentation, but we'll just continue. Before we are going to the Q&A sessions, I'd like to share with you the conclusion of today's webinar, looking back at some of the topics that we already addressed. So one of them is the need for higher data output. So that's one of the market drivers that I've mentioned. The personalization and decentralization of healthcare as the main drivers for hybrid integration, at least from our point of view. The second one is basically the need for collaboration and platform technologies. So innovation of individual partners as well as collaboration, making use of each other strength is key to enable all kinds of hybrid devices. Something that I haven't mentioned, but I have shown, is that obviously we need to collaborate on thinking outside of the box, mixing different form factors, making use of open platform technologies, and of course thinking out of the box in terms of materials to make full use of the economics of scale of each of the individual platform technologies. All in all, this leads to products with a higher value. Now, on this slide, I've depicted my contact details once more, so feel free to reach out after the meeting or after the Q&A session, not only to talk about potential business, but also about, I'd like to welcome you to invite or to contact me for potential collaborations, because making use of each other's strengths is key. All right, now I'm going to switch, so please give me 1 second. I'm going to switch to the questions which you've posted in your Q&A chat box, and I'm going to take a quick peek at them and address a few of them. And due to the time that we still have, I would say we would be able to handle 2 or 3 questions. All right. So there are quite a few interesting questions posted by many of you. Like said, I'm going to make sure that together with my colleagues, we're going to send around the questions and the answers to all of you. And I'm going to hit a couple of them. So the first one is actually, which actually comes back a few times. And I'm going to summarize the question as following. So the fluidic and electrical interfacing seems to be an important aspect when looking at the processes needed for hybrid integration. And the question is whether I can tell something about the possibilities and challenges. So yeah, of course. So we've already hit a few of them in a brief moment. So we need to provide connections to the outside world in terms of electrical connections, as well as fluidic connections, and I even presented an example of where a air connection, so a pressure connection, had to be made. So in terms of possibilities, when we're talking about electrical connection as a first factor, there are possibilities to add redistribution layers on top of your devices, connecting them to separate or individual components. Making use of wire bonding or conductive glues. Conductive glues in combination with pick and placing is a way to to integrate components, as well as the wafer level packaging example that I've briefly talked about, which is the integration of a TGV, a through glass via wafer, making use, for instance, on copper interconnections. Basically allowing an hermetic sealing at one hand and an electrical connection at the other hand. The other factor here is making fluidic interconnections. For instance, by integrating separate fluidic components, like the piezo-driven MEMS-based silicon micropump, or a valve, which can be basically separated into passive elements and active elements. I've shown an example of ways to interact, or actually to connect via top-down, making a hole, basically making a hole in the top layer of our device, or in the bottom layer. But another way is to make side connections, to make sure that the connections are coming out of the end of the sides of the device. But of course, what we have to take into account, which is a big challenge here, is that the next to the internal and external sealing, we have to take bonding into account. We need to carefully consider what kind of bonding technology is used, and whether that's compatible with either our hole or our side connect, and with the biology on chip, or the well, whatever we would like to integrate. A second question is well, it's actually, I think it's a very good one. I see it coming back 2 to 3 times. The question is, if I have to summarize it, it's the where does Micronet see the challenges in bringing the different parties and worlds together? I think here are also different aspects which we can all cover individually. So one of them is the technical point of view. So taking different materials, taking different form factors into account, that creates a technical challenge, and not we might be able to solve it, or a partner of us might be able to solve it. So we should always address the application individually. Then there is a difference, I guess, in business model of different parties. So the example of Fraunhofer collaborating with us on the MEMS based micropump is a good example of how you need to align business models, but also how you make use of the difference in business models to create value for both, or well, for the different parties. But it's definitely one of the challenges. The third one is a more more from a coordination or logistics point of view. Who is going to coordinate it, or who is going to be in the end responsible for the quality if we're talking about medical devices? Or it's an important one. And finally, there is the topic of IP. And because I see another question which I'd like to highlight, I'm going to stop now, because from the IP there is a good question from the audience. Thank you. The question is as follows: how does Micronet handle customer or third-party IP in such, well, more complex projects? Or at least that's how I would like to summarize it. Well, the answer is actually pretty short. We need to, and we strongly feel, well, that's already been done. Sorry. So again, I'm going to repeat it because I made a mess out of my answer. So the question is a good one. How does Micronet handle customer or third-party IP? And the answer is as follows. We need to fully respect the background IP of all parties involved. That can be the background IP of our the partners that we are collaborating with, but we should also take fully respect the application IP, which is more in the hands of our customers here. And what we do is we tend to agree on development agreements during our product development programs with the customers and with the third-party projects in how to deal with the new IP, because we also have to take into account that next to background IP, there's also foreground IP, which is generated basically as part of the collaboration with the partners or in collaboration with our customers. All right. So for the sake of time, I'm going to take all of your other questions and answer them offline and follow up on them. I'd like to thank you for your attention, and I wish you a very nice evening. And perhaps, well, actually, it's one more call out. This topic covered the hybrid integration of, or this webinar covered the hybrid integration of several components and materials. But if there are any topics that you'd like to that you would like to know a little bit more of, please don't hesitate to reach out to me. And well, basically we can either schedule something to brainstorm about new topics, but also feel free to bring in new ideas of topics that you'd like to see in a new webinar or even a new webinar series. So with this final announcement, I'd like to I'm now going to close off the webinar session of tonight. Thank you for your attention, and hopefully speak to you soon.